Section 8.4 is the last section we're going to do in Chapter 8, which is Systems of Equations and Inequalities. And we're going to look at matrix algebra. And we have 5 objectives here. The first is just find the sum and difference of two matrices. So we're going to work on matrix arithmetic. Then we're going to find scalar multiples, and we'll talk about what a scalar is of a matrix. Then we're going to find the product of two matrices, and that's the most complicated operation we do. Then we're going to find the inverse of a matrix. And then we're going to use that to solve a system of equations. And they have to be linear equations for this method to work, using an inverse matrix. Of course, all of this can be done now with computers, but you really need to know what the computer is doing to be able to give it good instructions. So recall the definition of a matrix is just a rectangular array of numbers. So they're arranged in rows and columns. And basically, this is what you're using if you use an Excel spreadsheet. You're putting things in rows and columns. Each entry in the matrix is called A sub ij, where I is the row and j is the column. And the matrix shown has m rows and n columns. So always count rows first and then columns. So matrices have their own defined arithmetic. So let's first look at sum and difference. And these go element by element. So the matrices have to have the same number of rows and columns. So they have to have the same dimensions, we say. And we represent matrix with usually a capital letter. So we'd say two matrices are equal by writing A equals B if they have the same number of rows and columns and each entry in A is equal to the corresponding entry in B. If they're the same size, then we can add the elements, or we can also do subtraction by doing the difference of the elements. So in this example, A plus B we can easily do because we have 0 and 4, so that's 4. 3 and 1, so that's a 4. Negative 5 and 0, so that's a negative 5. Then we have 1 and negative 2, so that's negative 1. 2 and 3, that's 5. And then 6 and negative 2, so that's 4. So this matrix is the sum of matrix A and matrix B. But if you try and add A and C, A is a 2 rows by 3 columns, and C is a 3 row by 2 columns. So this addition is not defined. So every matrix cannot just be added to every other matrix. Matrix addition is commutative. You can add in either order, and it's also associative, that as long as the matrix dimensions work, you can combine them, either the first two first and then the third one, or the second and third and then the first one, just like with numbers. So let's define the zero matrix as a matrix whose entries are all equal, and so that will have the property of, if you add a matrix with all 0 entries, it won't change your matrix. So it's called the additive identity. It works like the number 0 when we're working with real numbers, but it's a matrix. Okay, so the next thing we're going to do is find scalar multiples, and it's SCALAR. Scalar multiples of a matrix. So we're using a lowercase k to be a real number, and in this world where we have matrices are the objects we're working with, if we multiply something by just a real number, we call it a scalar so that we can tell it's something different than a matrix. So a matrix can be multiplied by a scalar by multiplying every entry in the matrix by that scalar. So here's some of the properties of scalar multiplication. It says you can multiply all the entries by some number h and then multiply them by the number k, or you can multiply k and h together first and then multiply each entry, which just makes sense if you think about we're doing real number operations here. And then it also works, you have to show this two different ways. I'll talk about that in a second. You can distribute scalar multiplication and get this logical looking result, but we have to write it two different ways because this first one says you can add the scalars together and then multiply, or you can multiply by each scalar and then add the two matrices together. Whereas this second one says add the two matrices together first and then multiply by a scalar, and you'll get the same result as if you multiply each matrix separately by the scalar. So we have to have additional properties because we have two kinds of objects, matrices and scalars, real numbers. So the thing that's going to be the most useful for us is to find the inverse, find the product first. So let's find the product of two matrices, and we're not going to actually use this except to check our answers for the last objective. But we'll do this in class because it's really helpful to see it demonstrated. But the idea being that it's a process of multiplying row vectors of the first matrix by column vectors of the second matrix. So it has some notation that goes with it. I find the notation is more confusing than just doing the operation. It is important that the dimensions work. So we can multiply C times A because C is a 3 by 2 matrix and A is a 2 by 3 matrix. So the result will be a 3 by 3 matrix. So these inner guys have to match up in order to do the operation, and then the outer two is the dimension of the result. So we'll do this in class, but I'll just write it out here. If I have 4, 1, 6, 2, negative 2, 3, I can multiply it by 0, 3, negative 5, 1, 2, 6. But AC, where it's the 2 by 3, by the 3 by 2, will give us a completely different result because it will be only a 2 by 2 matrix. So clearly, matrix multiplication is not commutative. So that's a theorem, actually. It's not commutative. And there are two properties, though, that do work how you expect. The associative property of multiplication, if all these multiplications work, it doesn't matter if you do BC first and then A, or AB first and then C. And the distributive property over matrix multiplication does work. So we have some more definitions. Entries along the diagonal of a square matrix, so only a square matrix has a diagonal. They're called the diagonal entries. And if you have a matrix where all the entries on the diagonal are 1 and every other entry is a 0, it's called the identity matrix, and it's I subscript where n is the size of the matrix. So this is a 4 by 4 identity matrix, so it's called I sub 4. This one is 3 by 3, so it's I sub 3. And what happens if you multiply by an identity matrix? Nothing changes. So that's what these next properties talk about. But you have to multiply by the right size identity matrix for the matrix multiplication to work. So an identity matrix is always a square matrix, and it behaves like the number 1 in the real number system, where multiplying by it doesn't change anything. Okay, so now we're on to the more useful part for us. Find the inverse of a matrix, and then we're going to use that to solve a system of equations. So you can only find the inverse of a square matrix. Not every matrix has an inverse. And if it doesn't have an inverse, it's called singular. If it does have an inverse, it's called non-singular. So the steps for finding the inverse, I'll show you the beginning of the steps on this example here. You form the augmented matrix where you keep all the entries you have, 3, 3, 1, 1, 2, 1, 2, negative 1, 1. Then you make a vertical line, and then you put the proper size identity matrix so that it matches the square matrix you started with. Then you're going to go step by step and transform this matrix into what we'll learn about called reduced row echelon form. And once we do that, then on the left will be the identity matrix, and on the right will be the inverse matrix. So it's somewhat tedious and you have to be very meticulous for the result to work out right. The nice thing is you can always check, because if you think you have found A inverse, you multiply A and A inverse together and you have to get the identity matrix. Or you can do it in the other order. This is the only time when matrix multiplication is commutative, is when you're multiplying a matrix by its inverse, and you should get the identity matrix either way. So we're going to use this idea to solve a system, because if we write our system of equations in a matrix multiplication form, it looks like A, the coefficient matrix, times X, a column matrix of the variables, equals B, the column matrix of the constants. And once we find the inverse matrix of A, then we can multiply on the front of each side by A, and using all the properties that we've just learned, we can see that if we take the inverse that we find and multiply it by the column vector of the constants, that will give us the result of a column vector that tells us the values of the variables. So we're going to use that to solve this, and I have a video that goes through another one so that you have another example, and it just takes some time and you have to be very patient and very careful. So that's the end of this movie.